Now I shall tell you the definition of secondary focus. Secondary focus, the definition I am telling, when a parallel beam of light rays coming obliquely to the principal axis of a lens is refracted through the lens, then after refraction, the light rays either converge to a point in case of convex lens or appear to diverge from a point in case of concave lens on its focal plane. This point on the focal plane is called a secondary focus. I am repeating the definition. When a parallel beam of light rays coming obliquely to the principal axis of a lens is incident on it, then after refraction, the light rays either converge to a point in case of convex lens or appear to diverge from a point in case of concave lens on its focal plane. And this point is called a secondary focus. The diagram is drawn here. You see, this is a convex lens. So in case of convex lens, this is a parallel beam of light rays is incident on the lens. After refraction, the light rays are meeting at a point f dashed on the focal plane, and this point is secondary focus. In case of concave lens, you see a parallel beam of light rays coming obliquely to the principal axis when incident on the concave lens. After refraction, the light rays appear to diverge from a point on the focal plane. It's a focal plane, you see f dash on the focal plane. It is appear to diverge from this point f dash, and so this is the secondary focus. So secondary focus here in case of convex lens on the focal plane, and in case of on the focal plane, this is a secondary focus. Now one thing is important, that secondary focus for a lens is not a fixed point. Primary focus or principal focus is fixed, but in case of secondary focus, any point on the focal plane may be a secondary focus, and the position of the secondary focus depends on the inclination of the incident rays with the principal axis. From which direction are the rays incident on the lens, this gives it that will give you the position of the secondary focus. So the position of the secondary focus is not fixed, although the position of principal focus is fixed for the lens. So this is secondary focus. Our next definition, another definition I tell you, the aperture of a lens. Aperture, what do we mean by aperture of a lens? Aperture means the diameter of the circular boundary of a lens is called its aperture. The diameter of the circular boundary, actually when you see a lens from the front side, it is circular, and the diameter of this circle is its aperture. Obviously, in those diagrams, the aperture is this one. For convex lens, this is the aperture. For concave lens, the straight line is the aperture. So, greater the aperture of a lens, more number of rays are refracted to it. So, with the increase of aperture, the brightness of the image formed by a lens increases. However, the sharpness of the image is decreased. That for another reason due to aberration or some defect of lens. It will be discussed in class 11 or 12. Now, I am just telling that greater the aperture, more rays are refracted and making the image more and more bright. So, is aperture. Next, we will discuss the converging and diverging nature of lens. Now, convex lens is called a converging lens and concave lens is called a diverging lens. Why is so? A convex lens is converging lens is light rays after getting refracted through a convex lens bend towards its principal axis. Always, light rays refracting through a convex lens bend towards its principal axis. The refracted rays always bend toward the principal axis. If a parallel beam of light rays are incident on a convex lens, after refraction they actually meet at a point, either at principal focus or on the focal plane, if a parallel beam of light is incident. So you see, the light rays are getting refracted and they are getting bent toward the principal axis. Bending of the rays is toward the principal axis. And that is why, as the light rays after refraction bend toward the principal axis, this is called a converging lens. And concave lens, in case of concave lens, light rays after refraction always bend away from the principal axis. That is, the separation between the rays increases all times. So, from the original direction, they get more separated. If light rays are refracted through a concave lens, then after refraction, the light rays get more separated and they bend away from the principal axis. And that is why if a parallel beam of light rays is incident on a concave lens, I've shown you that after refraction, they appear to diverge from principal focus or appear to diverge from secondary focus on the focal plane. So here the light rays are bending away from the principal axis, that is bending more from their original direction, and that is why concave lens is called a diverging lens. Now I discuss a question. You are provided with a question: when does a convex lens behave like a diverging lens, a concave lens a converging lens? Under which situation? When the surrounding medium of a lens, I provided you the answer. When the surrounding medium of a lens is optically denser than the lens material, then a convex lens behaves like a diverging lens and a concave lens is a converging lens. Only in this case, if the surrounding medium of a lens is more dense, optically more dense, only in that case they will behave oppositely. Now the converging and diverging action of lens can be shown. You see the follow the as I just said drawing the diagram. Here, the converging action and diverging action of lens, convex lens and concave lens, can be shown with the concept of prism. We know light rays when refracted through a prism. If if the prismatic is optically dense, I'm telling consider glass prism. So when light rays are refracted through a prism, if a light ray is refracted, the light ray on refraction on both refracting surfaces bend toward the base of the prism. So bending of the light ray occurs always toward the base, within the prism and outside the prism. So you see, when a light ray is refracted through a prism, the light ray always bends toward the base of the prism. And with this concept, we can explain the converging and diverging action of convex and concave lens respectively. You see, I'm just drawing the diagram for convex lens. You just think of a convex lens. This is a convex lens. A convex lens, any lens, not convex, any lens may be considered as an assimilation of a large number of truncated prisms. That is, their vertex are broken. So, truncated prism. So any lens may be considered as a assimilation of a number of truncated prisms, both convex lens and concave lens. For convex lens, you see, I'm just drawing the diagram. The truncated prisms. These are the truncated prisms. You see, these are truncated prism. This is one, Or this is a complete prism, this truncated prism, this is a proportion. And at the center, you can consider as a rectangular slab. At the center of a rectangular slab. You can follow the book. You can see the diagram clearly given in your book. Now, these truncated prisms are there. The number of truncated prisms. And in case of convex lens, the bases of the truncated prisms are towards the principal axis. That is, the bases of the prisms above the principal axis downwards, and the bases of the prisms below the principal axis upwards. That is, the bases are toward the principal axis. And if we consider a refraction through a prism, then in that case the converging action can be explained. I am just drawing as a parallel beam of light. I am just considering one or two rays. You just see one ray is considered parallel to principal axis, and actually refraction takes place on this side, on that point, and then this point. A bending toward the base, again a bending toward the base. So ultimately intersect the principal axis at this point. Similarly, this ray parallel to principal axis is refracted through the prism, bending toward the base, again bending away. You have to show the bending of the ray on both the surfaces of the prism. It is important, not from the central line. In most books, this is given from central line, but you have to show the proper bending on the both the surfaces, reflecting surfaces of the prism. Here the bending takes place in one surface and another, and they ultimately you see they are meeting at this point, which is called focus. We know there's a parallel beam of light rays, and that is why it is called a converging lens. The converging action can be explained like this. In similarity, in case of concave lens, I'm drawing the diagram. We can consider a number of truncated prisms here also, but here the truncated prisms are oriented in reverse direction. That is, in this case, the truncated prisms are such above the principal axis, the vertices of the prism are toward the principal. That is, the bases of the prism are away from the principal axis upwards, and below the principal axis, the bases of the prism are away from the principal axis, that is downwards. So here, in this case, bases of the prisms below or above the principal axis are away from the principal axis. So just opposite to those in case of convex lens. So here also, following the rule of refraction to a prism, you can draw the diagram. I'm just drawing the diagram. You see, I'm just drawing one diagram. You see here a parallel beam of light rays. Is a parallel beam of light rays. After so this is one ray and considered parallel to principal axis, and here after reflection it is bending away from the base of the prism, toward the base of the prism, and again here bending toward the base of the prism. So the bending is upwards away from the principal axis. Here also another ray considered parallel to principal axis, so it is a bending toward the base of the prism, again bending toward the base of the prism. So twice the bending occurs, and they appear to diverge from this point M. So this point is the principal focus of the concave lens. So thus the converging action of convex lens and diverging action of the concave lens can be understood clearly just with the help of the concept of prism. Just think of the prisms, truncated prisms, a sum of truncated prisms, and follow the rule of refraction through the prism, that is bending, always bending toward the base of the prism, and you can automatically draw the diagrams, the converging and diverging action of the convex lens and concave lens respectively. Next topic is a formation of image by lenses. Formation of images by lenses, and actually there are some refraction parts of some definite rays are taken to draw the diagram for the formation of images by lenses. And the refraction parts of which rays? The refraction path of those rays which are known to us. Just I am telling the refraction paths of which rays. We know when a light ray coming parallel to the principal lens is incident on it, then after diffraction to the lens, it either actually meets at the focus or in case of convex lens or appear to diverge from a point that is focus in case of concave lens. So we see that if we consider a one ray from any object parallel to the principal axis, then the refraction path of the ray is known. That is, after refraction, it will either pass through the focus or appear to diverge from the focus. Another ray, as our consideration is only thin lens, another ray we can consider a light ray coming through the optical center, is refracting through the optical center, goes straight without any displacement and deviation. So there is no. So we can just draw one ray from the object point to the optical center and it will go straight without any displacement or deviation. This is another ray. Another ray we can consider a light ray starting from the focus. Starting from the first principal focus, after diffraction become parallel to the principal axis. That can also be considered. However, we'll consider the first two refraction parts of the first two rays to draw the diagram. Now, in case of convex lens, there are many formation of images. There are actually six images. Out of them, all are not in your syllabus. We'll discuss the image formation, which are only within syllabus. A few, or selected one. The first one, actually, in case of convex lens, the formation of image, the nature, size, position of the image depends on the position of the object. The object can be brought from infinity gradually toward the lens, from infinity toward the lens, and at different positions, the nature and size of the image is different. In your syllabus, I'm just to mention three or four diagrams. There are in your syllabus there are three diagrams for convex lens and one diagram for concave lens. So I'm just studying the formation of image by convex lens. So what are those? First one is the formation of real magnified image by a convex lens. Real magnified image and diminished magnified image and virtual image by lens. These three are in your syllabus. So we'll just discuss one after another. First one is real magnified, formation of real magnified image. So in that case, the formation of real magnified image, I'm just considering convex lens. Real magnified image. Real magnified image formation by convex lens. Now in this case, the position of object is in between F and 2F. A convex lens forms real magnified image of an object while the object is placed at a distance more than focal length but less than twice the focal length. That is in between F and 2F. So position of object in between F and 2F. In between F and 2F. In between F and 2F. So position of the object is in between F and 2F. I'm just drawing the diagram. It's given in your book. I'm just for your explanation. You can follow the book. You can see the diagram in your book. For explanation, I'm just drawing the diagram here. You just with the scale, you draw Korean diagram you can draw. So draw the lens and take focal length on both sides and twice the focal length. Equal four equal distances, equal segments are considered. From the center of the optical center, that four segments, equal segments are drawn. So F and 2F. On both sides, you have to show F and 2F. Now the object is placed in between F and 2F. When drawing the diagrams, we are considering thin lens. Another thing, the object is considered to be placed perpendicularly on the principal axis, and here the object is placed in between F and 2F. Just object is placed in between F and 2F. One ray is considered parallel to principal axis. After refraction, it will pass through focus. After refraction, it will pass through focus. And another ray is considered through the optical center. I told you, and it will go straight. So you see, these two rays meet at a point beyond a distance 2F. So here AB is the object and say A dash B dash is the image. I've drawn the diagram. You see, one ray is considered parallel to principal axis. After refraction, it passes through focus. Another ray through optical center, it goes straight. These two rays meet at this point A dash. So A dash is the image of the point A, and it is, and similarly for the other points. So A dash to B dash, A dash to B dash is the image of the object. You see, the nature of the image is real. Nature of the image is inverted, real, inverted, and magnified. Real image, it is real image. If you place a screen here, the image can be obtained on the screen, is a real image, is the definition of real image. So, the image can be obtained on a screen, and so it is real image, and it is inverted. You see, it is vertically inverted with respect to the object, and it is magnified. The size of the image is greater than to the object. So this is the characteristics of the image, the nature and size, real, inverted, and magnified. And the only application of this image formation is a cinema projector. You can tell. A cinema projector, this principle, in a projector machine, the film is placed in between F and 2F, and the image is formed on the screen, which is placed beyond 2F, much beyond 2F on the screen, but the image is inverted, and that's why to get real image, sorry, erect image on the screen, the film is to be placed in inverted fashion. So within the projector, the film is placed in inverted fashion so that the image may become erect on the screen, and that is why this is the application of many other applications, the cinema projector, then epidiascope projector machine, epidiascope. In all these cases, this principle is utilized. The next one is the real diminished image. When the size of the image is less than that of the object. Real diminished image. I am just drawing the diagram and will explain. Real diminished image. In this case, the position of the object is beyond 2F. Beyond 2F, that is, the object is to be placed at a distance more than twice the focal length. More than twice the focal length of the lens. Beyond 2F. Object is placed at a distance beyond 2F. Object is placed at a distance beyond 2m. And the diagram can be drawn like this. I'm just drawing the diagram. The diagram is given in your book. You can follow the diagram in your book. You can understand. The object is placed beyond 2m. You see, oh, I'm drawing the diagram also.